All right, so welcome to week 4, so the payload environment. Today we're going to talk about the environments that your payload is going to have to experience and survive as well as operate in. But before we start, I want to give you a few Binar Space Program updates. So tomorrow our team is actually flying to Japan to hand over Binar 2, 3, 4. So there's 2, 3, and 4 right there. Oh, it's out of batteries. So 2, 3, 4 stacked on top of each other, and that's Binar 2, one of the flight models. You've seen those before. Whoops, this is really sensitive. So yeah, they're flying to Japan to hand the satellites over to the Japanese Aerospace Exploration Agency, or JAXA, and then those are going to get launched in August. So why that's exciting is when we launched Binar 1, that's our team there. We went and watched it at Yagan Square. Do you recognize where that is? Yagan Square. So we're not sure what we're going to do for the next launch, but the next launch is in August. And even though that's not the one that your satellites are going to, or your payloads are going to fly on, that's eventually where your payloads are going to fly. And we're going to launch them on a rocket up into space. And so we're hoping that in August you can come and watch that with us, with your team t-shirts and awesome team names and branding, because it's a really great event. So that's something that we'll want to do. And also, so there's Binar 1, but when Binar 2, 3, 4 are flying, we're actually doing a capture the flag competition. So if you can get your amateur radio license, and it's a global competition, you're going to try to send your call sign up to the satellite in orbit using radio frequencies and basically capture the flag with the whole amateur radio community. So a little capture the flag. So that's my call sign. I just got my amateur radio license. So it's VK6 meg. So I hope that's something you'll look into as well. So this week, we want to become familiar with the environments in which your payloads will need to survive and operate. Consider the design challenges they present to you. And discuss how you might deal with these challenges. We won't go into in-depth yet because you're still doing your payload concepts, but we will talk about that as the program progresses. So considering the pre-launch environment, not just the space environment, and the launch environments for your payloads, you may need to consider corrosion from the atmosphere. So we're at the equator, that's Arianespace with ESA, and you might worry about the components sitting out in humidity or heat before they get launched. And then actual launch itself is quite an ordeal on a payload. So if you think about a rocket launch, it's a lot of G's, it's a lot of vibration. You need to make sure you design your payload to be pretty secure and pretty stable, so nothing's going to crack or snap or break off. We do test for that, but when you're designing it, you want to make sure that there's nothing too delicate, so that it's really well made. So that's another one. And but not all launch environments are corrosive and humid. So this one is in a desert. This is in, I believe, Kazakhstan at the Baikonur Cosmodrome. So there are different launch environment or pre-launch environments and launch environments. We'll come back to launch. So this week we're just going to focus on the space environment as much as I can. But we wanted to remind you that space isn't the only environment you have to consider for your payloads, and we wanted to include some really nice pictures of rocket launches. So the primary considerations of the space environment. Can you guys tell me what some of the environmental conditions in space would be? Yeah, cold. So the thermal environment. And what other ones? What other environmental conditions? What else is space like that you know? Mr. Coe? Debris is another one, and that's concerned more for the spacecraft itself. And unfortunately, our CubeSats don't really have any evasive propulsion, but it is important to be aware of. But there's also the vacuum of space, so extreme low pressure, the neutral and plasma environment, which I'm going to try to explain at a high level because as I'm learning along with you as students, because I do not have a PhD nor am I a scientist, but I'm fascinated by all of this. And please, if you have any questions, send them to me and I will send them to my hive mind. But I just want to tell you about these environments so that you can start looking into them because there's some really cool phenomena attached to this. So this is a great book that I'm actually going to be dropping off to the school. I've got a copy for all the schools. This is just my library's copy, but I just love it because it gives us so much information about all kinds of different stuff from space, but this is the particles from space. So when we're talking about the ionosphere and the plasma environment, That is a really great reference. But I won't go too in depth into it for fear of getting it wrong, because I'm still studying. Magnetic fields and radiation, the thermal environment, so you're hot and cold, and the debris environment. 10 points, Mr. Coe. So again, applies more directly to the CubeSat, but good to be aware of. So the vacuum, what's a vacuum other than the appliance? Do you know what a vacuum is? Yes? It is with nothing. So space isn't actually a perfect vacuum. There is, especially at LEO, there is some atmosphere, and there are particles there, but it is an extremely low pressure environment. Lacks air or atmosphere, so very different from what we experience here on Earth. So why that's important to the design of your payload is there are thermal actually issues with that. So we experienced this. We sent a camera payload up on a high altitude balloon, and we went quite high up where the atmosphere isn't quite space, but very, very thin, very low pressure environment. And even though it was minus 40, our payload, one of the components overheated and didn't function as expected. And the reason for that is because, you know, at the ground level where we've got the air, you can use a fan, you know, the air can cool things off, but that doesn't happen up there. So the air actually doesn't convect heat away from components. So you have to radiate heat out. So, you know, using heat sinks or using other methods of getting the heat away from components that you want it to. There's also the issue of outgassing. So if you have plastic or something, so if you 3D printed a component using regular plastic and you put it in there, because it's got gases trapped inside in that vacuum, those are going to come out, and those can contaminate your lenses, it can contaminate your solar panels on the spacecraft, it can even contaminate other spacecraft in the deployment area beforehand, so you actually can't have any outgassing. So you've got to select materials that don't outgas. But again, don't worry about any of this just now. It's just good to be aware of as we move through. So, whoop. So yeah, low pressure, lack of atmosphere. And then if we have trapped air in a vacuum, what do you think will happen? So say we have a camera lens that has no vents, and there's air inside of it. And as we're launching even, not even when we get to space, but as we have rapidly dropping pressure and, you know, lower pressure, what do you think might happen to air that's trapped inside something?
It's going to try to escape.
Yeah, and what happens if it can't escape?
It's just going to break.
Exactly, so we're gonna have some fun with that later. So I brought along, but for now we'll just go through everything as best I can. So the neutral and the plasma environment, so the neutral environment in space is neutral gas particles. So while they don't react in the sort of highly charged way that plasma environments do, they can create drag on our spacecraft. So a lot of it, so the oxygen, there is still force acting on our spacecraft, and that affects our orbits and how long we're in orbit. So not something necessarily for your payload, but atomic oxygen erosion. So out in space, instead of having O2 like we breathe on Earth, we have just single atom oxygen molecules, and they're traveling really fast, so they can smash into things and cause a lot of degradation of parts. But they're also highly reactive, and so they'll react. As you can see here, this is a bunch of materials that were sent up by NASA before flight. So I'm not sure, you look like some might be brass or copper, different kinds of metals, plastics, and then that's after 4 years. And you would think that, down on Earth things are going to rust, but up in space you're like, oh, there's no air, so things don't rust. Absolutely they do. Well, oxidize. So that's quite interesting. So the neutral and the plasma environment. Space around Earth is the plasma environment, and consisting of free-floating electrons and ions. Have you learned about ionizing? Yeah, in science? Yeah? Yeah, and what do you understand? What's an ion? All right. Well, that's all right. We don't have to. That's great. We'll look more into it, but it's your charged particles, right? So you've got lots of electrons floating around, you've got lots of protons floating around, but the protons are big and slowly move, so we concern ourselves more with the electrons. But effectively, you get a really highly electrically conductive environment out in space. So you can get arcing happening between sections of your payload, so everything can, you can actually get electrical damage, but it's really quite interesting. And those particles that are out there are influenced by the Earth's magnetic field. So down on Earth, an example would be neon signs. So once you put the ions in a tube, or the ions of gas, and then you put energy through it, it lights up, and then you get neon signs. Plasma TVs, lightning is an example, a visual example of ionization. So there's plasma TVs. And there's an example of basically a coronal mass ejection from the sun. That's what can send lots and lots of ions towards us in the Earth's atmosphere. But then when the ions in the plasmasphere hit the Earth's magnetic fields, they go around and they get channeled towards the north and south poles, and you get the aurora borealis, because that's the effect of those ions reacting with either oxygen or nitrogen, depending on which ones they hit, and you get these beautiful colors and light up. So something I found out as I was falling down lots of rabbit holes researching this week's lecture was that we are approaching the peak of our current solar cycle. So the sun, the magnetic north and south of the sun basically switch places every 11 years. So in the middle of that cycle, you get the most activity of sunspots and flares and crazy space weather, and this year is that. So that's why everyone's flocking to the auroras right now, is because there's a really crazy amount of activity happening, and there's some really great links on that sheet I gave you if you want to go learn more about space weather and solar flares, and keep an eye on that stuff. So it's very, very, very cool. So the reason it's important to your payload is it can corrupt data, it can damage components, so you need to make sure that anything sensitive is shielded, basically. But we'll talk more about that later. And the magnetic fields and radiation, Earth is surrounded by a magnetic field, which I'm sure you know about, and it creates a complex radiation environment in space. So we get the Van Allen belts because the free-floating radiation in space gets channeled into certain areas, and again, it can affect materials, degrade materials. If you're trying to gather data in space, it can corrupt your data. So these are all things that you need to be aware of, but we'll learn more about as we go, because I realize it's a lot of info. And yeah, the thermal environment, the payload and the cube satellite will be subject to both extreme hot and extreme cold, sometimes at the same time, because if the side of the CubeSat that's facing the Earth is dark and the other side's directly exposed to the sun, they're going to be sort of hot and cold at the same time. But I'll give, we have some information on how the temperature inside is, but you need to make sure that the components you select can operate in the temperatures that you're going to get out in space. So you can look into different components. There's we're not worried about human comfort because there's no people inside the CubeSat. You just need to make sure that whatever temperature we're going to experience in orbit with your payloads, the components are designed or at least tested to those extremes, because sometimes we've actually been able to push the boundaries of what what the data sheet says or the instruction manual says, and we've been able to have things survive a little bit better than we would have expected. Boop. And the debris environment, as Mr. Coe mentioned, more of a concern for the CubeSat itself, because that might have to, get dinged by little things occasionally, called conjunctions. Hopefully they don't happen to us. But it's worth discussing because the Binar itself is designed to, as most CubeSats are, to burn up on reentry and not contribute to the increase in space junk, and there is a lot. And low Earth orbit is actually, growing. There's more and more debris all the time. So I'll show you this neat little website, which is again on your resources sheet. This is called Leo Labs. So they're a company that basically monitor the Earth orbit environment, and this is a visualization of low Earth orbit, and it's actually a really fun website to play with because you can go, it's got all the satellites there. See all those little green things? Those are all satellites, and you can click on them and find out what they are. And then you can go on the SatNog's website and you can find out more data about them. But if we go around to Australia, and there's a little checkbox there, and I'm going to click on its debris. It's sort of depressing, but yeah, there's a lot of space debris, and those are only the ones that are tracked. So go and have a look at that website, and definitely worth having a look at. So, how objects behave in a vacuum. This is where we're going to have a little bit of fun with a hands-on activity. So I'll just stop the video because I'm going to not spoil the fun for all the other schools who are watching this online, who I will bring this activity to when I come see you in person. So thank you for watching. I'm going to turn this off.